Hello everyone, welcome back to another video of our multi-threading in Java series. This is part 2 of our Dining Philosophers Problem, where we will actually code this problem in 4 different ways starting from beginner to production ready solution. Before you continue, it is highly recommended to go and watch the part 1 of this video. I have linked part 1 in description and on top of this video as well. In part 1, we covered the theory part, we understood the problem, learnt about all the edge cases like deadlock, starvation, live lock and race condition that we need to handle while coding. If you have already watched part 1, then without wasting any time, let's dive into coding. Let's start coding our naive solution. Let's first create our philosopher class. So philosopher is a thread, therefore we'll go ahead and write implements runnable. Correct. Let's implement the run method. Before that, what are all the resources that philosopher will have access to? So the first is, let's give philosopher our ID, and the resources will be two forks, the left fork and the right fork, right? Object left fork and right fork, right? Now let's go ahead and create the constructor. Correct, this is our constructor. Then our philosopher has two tasks. The first task is to think and the second one is to eat. So let's simulate both thinking and eating of philosopher. So one method will be think and another method will be eat. Right? Inside thinking, what we'll do? We'll just randomly wait for let's say 1000 milliseconds. Correct? Right? And let's do thread dot sleep 1000. Similar will be the case for eat. Right? Philosopher is eating and right. So these are the two methods. Now inside the run method, what we have to do? Indefinitely, our philosopher needs to think, then acquire the left fork, acquire the right fork, eat, and then go back to thinking, right? So what we'll do is, we'll write a try catch block, right? Inside our try catch block, we'll do an infinite loop where first the philosopher will think, right? After thinking, what will philosopher do? Acquire the left fork, right? If left fork is acquired, let's print philosopher picked up left fork, right? And once the left fork is acquired, we'll go ahead and acquire the right fork, right? After acquiring both the forks, philosopher will go ahead and eat, right? After eating, it will release the right fork, then left fork, and inside this while loop, it will go ahead and think again, right? So this will go on indefinitely, and this is our philosopher class. Now let's write our main class. Inside our main class, what we'll have? First, the number of philosophers. So let's take the number of philosopher and forks to be equal to 5. Then we'll go ahead and create 5 forks, right? So object let's initialize this forks. Now let's create our 5 philosophers thread and pass in the respective forks, respective left fork and right fork to that philosopher. Right? Inside this, what we'll do? We'll write philosopher. What will our philosopher take? First, the philosopher will take the ID. Let's put it in front, right? So first we'll pass in the ID, then the left fork. What is the left fork? The left fork is fork I, and we saw on our blackboard the right fork is fork of I plus 1 modulo n, right? So this is our philosopher. Then let's create a thread and pass in philosopher inside it, right? And post that thread dot start, right? So we have created 5 different threads. Thread dot start. We have passed in the left fork and the right fork. Now this is the naive solution. If I run this program, we might not see the deadlock, but deadlock is present here. And why the deadlock is present here? I already explained that on blackboard, right? So the 4 conditions all are satisfied here, correct? So let's go ahead and run this first. This is the broken solution. You might see deadlock, you might not see deadlock. Currently, we are not seeing deadlock, but if we run this indefinitely, some or the other time, this program will come at halt, right? So let's stop and see what is happening. Initially, all the 5 philosophers are thinking. Then philosopher 0 has picked up the left fork. And once philosopher 0 has picked up the right fork as well, left fork and right fork, post that only philosopher 0 goes to eating. For philosopher 3 also, if you see, philosopher 3 has picked up the left fork, then right fork, and post that it went to eating, right? So philosopher 2 has picked up the left fork, but for the right fork, it has to wait for so many cycles. When it acquired the right fork, it went ahead and start eating, right? So this is how our program works. Now this program has a problem which is known as deadlock. Let's go ahead and solve that deadlock. Now to solve the deadlock, what are the things we can do? There are 2 things that we can do. Let's go on our blackboard and see how we can break this deadlock. So deadlock follows this 4 condition, right? So let's try to break one of the condition. In our case, let's try to break this circular weight condition, correct? Why this circular weight is occurring here? The circular weight is occurring here because each and every philosopher is picking up the left fork first, right? What if we go ahead and change the order for just one philosopher, right? So what we'll do is, let's erase this. This is very interesting. What we'll do, we'll ask philosopher 1, okay, you can go ahead and pick up the left fork. P1 also you can go ahead and pick up the left fork. P2 also, P3 also. But for P4, instead of left fork, we will tell that if that is the 5th philosopher, then that philosopher will first of all try and acquire the right fork, right? If it gets the right fork, well and fine. If it doesn't get the right fork, it just waits for this fork to be released. And therefore, this F4 fork becomes empty and P3 is now able to acquire it. Correct? So P3 will acquire both F3 and F4, eat and then release these forks. And once P3 releases F3, then P2 will be able to use this, right? Similarly, when P2 releases F2, then P1 will be able to use this and so on, right? So if we change the order of picking up the forks for at least one of the philosopher, then we will have some progress and there will be no deadlock. So let's write this logic in our code as well. So in our code, let's create a new package, name it as solution1. And in this solution1, we'll also have 2 classes, which is main class and the philosopher class. Right? Now, this main class and philosopher class will almost exactly be the same with just one tweak. What that tweak will be, let's see. First, let's copy this, right? And the main class also, let's go ahead and copy this. Now what? Now for the last philosopher, we'll have to go ahead and change the order of picking up the fork. So let's go ahead and take a fourth parameter here. Boolean is last philosopher, right? Let's create here as well. And here this dot, right? And in our logic, what we'll do, we are thinking then left fork and right fork. Instead of that, what we'll do, if this is the last philosopher, right? If this is the last philosopher, then we will first pick up the right fork and then we will pick up the left fork, right? And else what we'll do, we'll do what we were doing till now, left fork and right fork, right? So we have changed the order. Now we have to pass this from our main class, correct? So what will be the last philosopher? Last philosopher will be when I will be equals to n minus 1, correct? So this is our code which handles deadlock. Very simple, right? The same code, and we have just passed in the variable and it works, right? So in this code, there will be no deadlock even if we run this program indefinitely, right? Because we have broken the condition, the circular weight condition. But there is a possibility that there can be starvation here, correct? Every time, suppose P0, P1, P2 and P3 are able to acquire the forks, eat, and then keep it, then again acquire the forks, correct? So if same set of philosopher acquires the forks again and again, the starvation is still possible here, right? So we'll see how we can solve this, but for now we have solved the deadlock condition, right? There is also another way in which we can solve this deadlock condition. So what we can do, let's go ahead and see that. So another way in which we can break the deadlock is by breaking this condition, hold and wait. How we will do that? So instead of all the 5 philosophers trying to acquire the fork, we will restrict the number of philosophers to 4, right? So at a particular point of time, only 4 philosophers can acquire the lock. So suppose we prevent P3 from acquiring the lock in the first cycle. So if we prevent P3 from acquiring the lock on F4 and F3, so what will happen? P0 will take the left fork, P1 will take left, P2 will take left, P3 will take nothing because we have stopped P3 from acquiring anything. P4 will acquire F4. Now this F3 is free and F3 can be acquired by P2, correct? So here also we have made sure that at least one thread progresses, right? So P2 will acquire both these forks and eat, correct? And as soon as P2 keeps this fork, P1 will be able to pick up F2 and the progress continues, right? In another cycle, there can be a case that P3 gets the chance and P4 doesn't, right? But at any particular point of time in one cycle, instead of 5, only 4 philosophers will try to acquire the fork. So we'll get progress as well, right? And how we can restrict that? We can restrict that using semaphore. Let's see in our code how we can do that, right? So let's create another package, solution2, and this solution2 will also have 2 classes, the main class and the philosopher class. Here also philosopher will have almost the same code. So let's first go ahead and copy this. And main class will almost have the same code. So let's go ahead and copy this as well for now, right? In our philosopher, we are trying to restrict the picking up of forks to only 4 philosophers, right? One less than the total number of philosophers present. So for that, what we'll have? We will need to have a semaphore. So if we have a semaphore, let's name it the dining semaphore, right? And add it to the constructor. What we'll do initially, before acquiring the left fork and right fork, we'll just go ahead and do dining semaphore dot acquire, right? We'll write this in try catch block. Reason is we always want to release the semaphore which we have acquired, correct? And in our finally block, we'll go ahead and write dining semaphore dot release, right? And in our main class, let's create a semaphore equals to new semaphore, and this semaphore will have 1 less permits than the total number of permits present. And inside our philosopher, okay, so let's remove this first. And inside our philosopher will pass in this dining semaphore, correct? So this semaphore is fast. It has only 4 permits when n is equal to 5. So 4 of the philosophers will go ahead and acquire the semaphore. So 1 will be left, right? Therefore, at least one philosopher will progress ahead and our progress continues. So again, we have prevented the deadlock, but this time, what is the Coffman condition that we are breaking? We are breaking the hold and wait, correct? So if I go ahead and run this, it runs perfectly fine. Indefinitely also, if we run this, there will be no deadlock here as well, correct? But again, there is problem here. So in our first solution also, we have broken the deadlock, but we have not solved starvation. And here also, we have not solved starvation. There might be a possibility that every time the same 4 philosophers are acquiring the semaphore and then eating and then releasing the semaphore, right? So to solve this starvation as well, we have a third solution, and that third solution is a little bit complex, but it is based on reentrant lock and condition. So let's see how we can code that third condition. So the third solution is a little complex and I have coded it already so that we can focus more on understanding how it works. And I advise you all to code the solution first on your own and then proceed with this section. So let's first see the idea behind it and the pseudocode before diving into the code, right? So what we'll do here, instead of acquiring the fork directly, we will use a try lock method of reentrant lock and we'll try to acquire that fork for some particular timeout. We'll try to acquire the lock. Then if that fork is not available within that timeout, then we give up and we release any other fork if we are holding, right? And then we try again later. So what this will do, we are not holding on to something. We are not holding and waiting on the fork. If it is not available in a timeout, we are releasing it. Therefore, we are breaking the Coffman condition, which is hold and wait, right? Now, if somehow we are able to acquire the first fork and the second fork we are not able to get in the particular timeout, what we will do? So we will release the first fork also, right? So no holding while waiting and therefore no deadlock. So the pseudocode will be, for every philosopher, first the philosopher will think. After thinking for indefinite amount of time, it will try to acquire the left fork with a timeout. If that is acquired, then acquire the right fork with the timeout. And if the right fork is also acquired, then you proceed to eat, right? And after eating, you release the right fork first, then the left fork, and then you break, right? Now what happens? You are not able to acquire the right fork. If you are not able to acquire the right fork, you go inside the else and you release the left fork, and post that you wait for random amount of time. Now this is very important. Why we have put a random amount of time here? If we don't put random amount of time here, and suppose if we wait for 1000 milliseconds, fixed 1000 milliseconds, there is a possibility that all the philosophers, they go ahead and acquire the left fork, right? And they are not able to acquire the right fork. Then they wait for 1000 milliseconds and then they again go ahead and do the same process again and again, right? So they are live, but they are not able to make progress because no one is able to acquire the right fork, correct? Why? Because we have kept the timeout, here wait timeout same, 1000 milliseconds for every philosopher, right? Therefore, to avoid live lock, what we'll do, we will wait for random time here, right? So that at same time, they don't go ahead and again check whether left fork is present or not, right? That is why we have used random time here, correct? Now let's look into our code. So we have created a fork class, and inside the fork class, we have a lock. And picking up the fork means acquiring this particular lock. So what are we doing here? Right? So we are doing lock.trylock and we are giving a particular timeout. So for this amount of time, go ahead and wait. If you are able to acquire the lock, that means you have picked up that fork, right? And then you return true. That means you have picked up the fork. Now, if you want to put down that fork, you go ahead and do lock.unlock, right? You release the lock and you write, we print philosopher has put down that particular fork. In our constructor, we have passed in the philosopher ID, timeout, and the time unit, correct? So this is our fork class. Now in our philosopher class, what we have done? In our philosopher class, we have two forks, left fork and right fork. This is also same. This is also same. We have deliberately used a random timeout here so that we do not have live lock. After that, inside our run method, what we have done? Each philosopher is thinking first, right? Now we have this another while loop, while not 8. This is very important for starvation not to occur. We'll come on this while loop later, but first let's look at this logic. We have tried to acquire the left fork with a particular timeout. If we got the left fork, then we are trying to acquire the right fork as well. If we get the right fork, then we will eat, right? And post that, after eating, we'll put down the right fork, then the left fork. We'll mark this 8 is equal to true. That means this philosopher has eaten, and we'll break out of this loop, right? There can also be a case where it is able to get the left fork, but not able to get the right fork. If it doesn't get the right fork, what it will do? Couldn't get the right fork, so it will release the left fork as well, right? Breaking the hold and wait condition. And to avoid live lock, we are using random sleep here, correct? Now one more thing. Why this second while loop? While not 8, right? So without this while loop, if philosopher doesn't get the left fork, then without eating in the first cycle, what it will do? It will just break out of this. All these conditions won't be satisfied, correct? It will not get the left one. It will go ahead and wait for some time, and it will go back to thinking without even eating once, right? So to make sure in every cycle, every philosopher gets a chance to eat, we have kept this while loop, correct? So if the philosopher doesn't get the left fork, instead of going back to thinking, what it will do? It will go ahead and retry again immediately after this random timeout, correct? So that is the reason we do not want a philosopher to go back to thinking again and again. Therefore, we have used this second while loop, right? Now this think function and eat function are exactly the same. The only difference is we have used the random timeout here for sleeping, correct? Now let's go ahead and run this and see our output. So if I run this, again, this program goes on indefinitely. And the best thing about this program is it doesn't have deadlock, doesn't have starvation, doesn't have race condition, and doesn't have live lock as well. So out of these 4 solutions that we have written till now, the naive one, solution 2 and solution 3, let's see a final table of what each solution gives you, right? So in our naive solution, were we able to resolve the deadlock? No, we were not able to resolve the deadlock. What about starvation? Starvation also we were not able to resolve. Live lock, now since deadlock was present, so live lock was not present, correct? So live lock we were able to resolve. And Coffman fix, we didn't do any Coffman fix, right? All the 4 conditions were satisfied. Now in first solution, without semaphore, were we able to resolve the deadlock? Yes, we were able to resolve the deadlock. But what about starvation? So not completely, right? Starvation was still possible here, correct? What about live lock? Live lock was not present here. And what is the Coffman fix that we did? Coffman fix we did, and we were breaking the circular weight, right? Circular weight condition we broke here. Now the solution to the semaphore solution, what we did? We broke the deadlock, correct? Was starvation possible? Yes, starvation was possible there as well. What about live lock? Live lock was not possible. And Coffman fix? Yes, we did the Coffman fix and hold and wait. This was the condition that we broke. What about the third solution? Deadlock was not present. Starvation? Starvation also, using that internal while loop, we resolved this starvation. Live lock also, using random timeout, we resolved live lock. And Coffman fix also we did. What is the Coffman fix that we did? Again, we broke the hold and wait condition, correct? So this is the most preferred solution in the interviews, but you can start with the naive solution and then move ahead to solution 1, solution 2 and solution 3 depending on how much time you have in the interview, right? Okay, so I hope you understand this dining philosopher problem. That's it for this video, guys. If you like the video, please like, share and subscribe to my channel. I get more motivation to create more such videos. So that's it for this video. Until the next video, stay safe, stay healthy. Bye bye.